Hey guys, so I'm Manish. So I'm also one of the co-devs here at Server Labs, of course, building the MOI protocol. So as Rahul went into consensus, networking, and the state management layer, so I mostly focus on the execution and the logic runtime specifically. So we'll just talk a little bit about that today. So obviously, there's a session later today where we're going a little bit more into the development side of things, where I show you how to write the logic with our programming language, which is called Coco, and how the execution works in our own runtime called PISA. So I'll get a little bit deeper into that later today, but today we'll just talk about it more from a blockchain perspective on what logics are, right? So as I said, so I'm not going to do much of a demo here. I'm going to save that for the evening. So we're just going to talk about it from a conceptual perspective. So like I said, logics are basically just a collection of routines, internal state, and funds, right? So this sounds a lot like smart contract, right? But what makes it different is the fact that logics in MOI, unlike smart contracts in Ethereum or other platforms, can be managed and operated by people who deployed it, right? In Ethereum, once a smart contract is deployed, it just kind of becomes part of the system, right? The other most important part is because logics are native values and they're understood as a deeper concept beyond just a simple executable code, they're also upgradable, right? So because of our composite data structure, we can upgrade logics within an account and we can address them in a native way. Today, people do upgradability in Ethereum using namespace services and all these app-centric ideas that kind of create a bottleneck. But for us, we can upgrade logics, no problem, quite straightforward to do so. Obviously, upgradability is not supported in the Babylon network, but it's a feature coming soon. The other most important part of logic deployment is that traditionally speaking, when we deploy a smart contract, we deploy some simple bytecode, and in the EVM, the entire bytecode executes for every single call. But in our case, we have something unique called a manifest, which is basically this YAML or JSON file, something human readable and inspectable that is always deployed on chain. So many people or smart contract developers might be familiar with the idea of having to store their ABI with them in their application. You don't have to do that in MOI because the ABI is a verified part of the chain data. So when you deploy a contract, the contract is invocation interfaces, the bytecode, and the runtime of choice are all deployed all at once. Notice says something interesting there. Runtime of choice, right? That's quite important, right? So what we ended up doing with MOI, with the logic and the execution architecture, is that we decoupled the idea of executing interactions from the idea of executing the logic itself, right? So in the Ethereum virtual machine, everything happens inside the EVM. So the EVM is responsible for validating transactions, performing the state transition, running the actual bytecode of the user, everything. But in MOI, we kind of split that up. We, both Rahul and Ananta discussed the ISM. So the ISM kind of responsible for handling the interaction execution itself. We looked at a bunch of different types of interactions like creating assets, minting assets, burning them. We can deploy logics. We can invoke logics on them. And we have a whole plethora of interactions planned for the future. You can do things like staking and even governance and simple community-based interactions. Also, we can make them native. And over time, what people can build as smart contracts or applications on the chain could become interactions and natively understood by the protocol. The beauty of interaction-based idea is that when you have a transaction, it's a general purpose envelope for information state transition. But when you have an interaction, it's a very specific kind of value transaction, right? So when you're generating proofs or when you're trying to secure the network around a transaction model, it's very difficult to generate proofs on a general purpose level, much easier to do that on a specific purpose level, right? It's very easy to generate the proof that I'm just transferring X amount of tokens between two people compared to saying something could happen between two people. Let's find proof of that this happened, right? Much easier to do that when you look at it from an interaction perspective. The other important thing, and by actually separating the logic runtime and interaction execution, we also ended up separating the state management from the logic execution itself. This allows MOI to have a very flexible state management approach. Traditionally in smart contracts today, we have what we call persistent state, a state that is managed by the contract itself. This state is great because it makes contracts capable of storing information that they can only access one at a time, right? There's no way for this state lock to break. But it also becomes a lock, a bottleneck of sorts, right? So when someone's talking to a smart contract, no one else can talk to a smart contract. This becomes a huge bottleneck for application-based chains right now. For us, we support persistent state contracts if you really need it. Our point is that you don't really need it, but then if you do, it's possible. But what we introduced that's something completely unique is something called ephemeral states. It's the idea that the state is owned by the participant itself, not on the contract. And the state can only be managed and accessed by the logic when the participant interacts with the logic, right? So this is completely a new paradigm idea, right? Like think about the fact that my data is mine, And it only becomes accessible to an application like, say, Uber or Ola when I interact with Uber or Ola. On a normal basis, Uber or Ola cannot do anything to my state. This is revolutionary in itself. So that's how we enable, a true peer-to-peer execution model. Because now that the state has moved to the participant, that same logic, which was previously locked to just interacting with one participant, can now be invoked by hundreds of participants at the same time. All of them talking to something that's basically just code, which is managing state on the person who invoked it rather than on itself. So this makes it completely scalable in that sense. So you don't have to worry about locking and you don't have to worry about scalability. You can build applications that can manage thousands of people at the same time. Hundreds. It's really a matter of just, how scalable the network gets at that point. And I did mention that we separated the logic runtime. And what we're doing there is some of the fundamental problems that today's platforms face is that when they run across an issue with security or scalability with their virtual machine, they're not able to upgrade it because the entire chain history depends on the fact that that machine deterministically executed that transition. So they can't just change the EVM to be something else. It's not possible. So what we did is, because we decoupled the idea of interaction execution, logic runtime is now completely upgradable. And we support multiple logics and upgradable runtimes. So one of the one that we support today in Babylon is called PISA. It's a register-based virtual machine. And the reason it's register-based is, unlike the EVM, which is just numeric-based, PISA supports rich data types. So it supports collections, strings, bytes, addresses, all as natively in the runtime. They're not just numbers, simple stack-based machine. So, and the second important part of PISA is that the idea of the participant, the sender, and the participant's context, the resources in the computation. And the interaction itself is another resource in the computation. There's literally an opcode called sender, which will give you the participant's context object, and you can access fields and manipulate those data inside the runtime. There's another runtime, which I've not mentioned here, which is Meru, which is a WASM-based runtime, which will, enable, everyone's talking about WASM is the new, unicorn in Web3 space. So, WASM-based virtual machine, which will allow a lot more sandboxing, portability across other platforms. That's going to be Meru. And Hanoi. This is kind of something that we're aiming to do over the next few years. It's quite far-fetched, of course, but it's basically the idea of a cooperative compute model. Basically, I'll give you a thought exercise that will help you think about Hanoi, maybe, if you have time for it, sure. But there's a concept called general multi-party compute, which basically a bunch of machines come together to compute an output on some data, and they do it in such a way that not all of them need access to all the independent individual data, right? It's kind of complicated to think about, but this is an idea that became possible recently because internet and latencies and networking has become making it possible to do that in real time. It doesn't take forever to communicate data at that kind of speed anymore. So, thought exercise for someone, let's say there are 5 people who want to compute their average salary between them, right? Now, salary is usually confidential information. They don't want to reveal to each other what exactly each of their compensations are, but they want to compute the average. How do these people do it? Today's Web3 answer is, let's find a trusted third party, send him all the data, he'll compute it and send it back to us. So none of each other did not find it, but there is a trusted third party who's doing the work. Keyword, trusted. Assume you don't want to trust anybody. How do these 5 people do it? So this is a little bit technical, but the idea is each of these 5 people will split their individual numbers into 5 random size bits, and then they will propagate it to each other. And now when each of them sum up their parts, they have 5 values which mean nothing. So each of them now have a value that has no meaning on its own. But when you compute the sum of these values, you get the sum of everyone's compensation. You've just computed the sum of every person in the room's compensation without revealing anybody's individual compensation, right? Now, divide that by the number of participants, it's 5, it's your average, right? So this is the idea of multi-party compute. And Hanoi is a dream towards a general purpose multi-party compute. And why do we want to do that? Today, Web3, everyone wants to make it about ZK proofs. Everyone wants to generate zero-knowledge proofs to prove that everything is private, everything can happen off-chain quietly without people accessing the data. You can do that much better and much more performantly with something like Hanoi and multi-party compute, right? And it's much more scalable because generating the ZK proof probably takes longer than the execution itself. And last part I want to talk about is Cocolang, which is our own statically typed high-level context-oriented programming language. Context-oriented sounds new because it is. It's evolution on the idea of resource-oriented programming, which itself is an evolution from object-oriented programming. The idea is that the participant, the interaction, the context, and all of those things that we're talking about in terms of bringing context compute into computation and participants as dimension CocoLang can handle all that. And the most important part of CocoLang is that it's not designed to necessarily give you a lot of power. It's designed to take away responsibility from the developer in terms of managing security, right? CocoLang takes care of all of that for you. It'll make sure that you can't make bad loops. It makes sure that you don't access variables you're not supposed to. It makes sure you can't make a transition without intending to do it. The most important part of Coco, and stay tuned for the evening session where I'll show you how Coco looks and how it works, is that you cannot do something in Coco without intending to do it. Coco will never make a decision for you on behalf of you. Everything you write means something, and everything you want to do has to be written and meant, right? So this is something very important for blockchains, right? In Solidity, it's very easy to make an accidental line of code that does something you never intended to. It's very difficult for an auditor or someone who's inspecting the code, which is the most important part of smart contracts, by the way, to be able to verify that the code executes in the way it does. It has to be easy for auditors to look at the code and say, I'm quite sure this is exactly what it does. Today, this is not quite so easy with any of the programming languages I've seen personally. And Coco is our aim towards opening up that kind of idea, right? Making sure that auditors and people who are inspecting bytecode and verifying its execution can actually do that. And that's part of the manifest idea I mentioned, which is that the artifact you deploy is not just bytes. It's a readable file. It's human readable bytecode that you can actually verify. Even you don't need to be a machine level programmer to understand it. The bytecode is quite fairly human readable. So it's quite high level in that sense. But yeah, that is basically a high level overview of Coco and logics generally. Stay tuned to the evening session for a much more deep dive on logics, CocoLang, and we get to write a logic and deploy to the chain and see it there. Yeah, cool guys, thank you.